So this is part 2 of the Sigma Delta ADC converter, and in this video we're going to be talking about how it actually works. In the last video we're seeing some terminology, so let's get right into it. Okay, so as we saw in the last one, this was the shape when we applied the Sigma Delta ADC converter to a noisy signal, and as you can see in our band we had very little noise, and outside of it we had lots of. So first I'm gonna show you the transfer function and exactly how that works. Okay, so here we have the transfer function, and if we try to write it, so here we have the signal x, so here we have x minus y, and when it enters into the analog filter, we have this right here, and in the end we're gonna have y equals this right here, where q is the noise. And so after, if we want to just separate y and solve for it, I'm gonna do some simple algebra. Okay, so now I'm gonna move it to the other side. Now while we're here, we can do a common denominator directly. So this will be epsilon f minus epsilon divided by f. We can take epsilon in front of the parentheses, so we will have, sorry, this is a plus, and we can do a common denominator on the right side too. So now we just want to leave the epsilon on the left side, and as we can see, f and f cancels out, so we are left with epsilon equals x. We are left with two terms, and here it's by mistake I forgot to add an f from before. So this here is basically a signal, and here this here is the noise term. Now why this works is, let's say if you want to take lower frequencies, so when f is 0, so if we take the limit of the first term, we will have x divided by 1, so x, so we basically have just the signal. But if we take the limit of 0 for the second term, we will have 0 divided by 1, 0. So basically what this means is that in lower frequencies there is no noise and almost everything is signal. And if we want to take at higher frequencies, so let's say infinity, in the first term we'll have x divided by infinity, which is 0, but in the other term we'll take f in front, so here, and this cancel out, this term goes to 0, so we have q. So in higher frequencies we have just the noise. So this is the whole point on the Sigma Delta ADC, that in higher frequency you just have the noise, and in lower just the signal. And now the real circuit, how it looks. So this first part right here, this is the Sigma Delta ADC, and then it gets fed into a digital filter and decimator. So let's just look at the first part for now. So here we have a summator, we have a V in that goes into it, and we subtract here by reference voltage, so either it's plus Vref or minus Vref. We'll get into that later. And first, this new signal that we got here, it's the error signal. So when we have feedback, it's usually we're subtracting because something happened that's an error. And this part right here, the error signal, gets fed into an integrator, and an integrator is basically what does the noise shaping, this little weird noise shape that was like this, that was a big advantage. After we integrate the signal, it goes into a comparator, which is this part right here, and if the voltage of the integrator is bigger than 0, because here we are comparing to 0 since it's connected to ground, then we have the output of the comparator that is equal to 1. If it's smaller than 0, then output of the comparator is 0. And as you can see here, we have a feedback loop that goes into a 1-bit ADC. We need an ADC here because right here V in is an analog voltage, so also this we want to be an analog voltage, because you can't just subtract digital from an analog voltage. You need both to be or analog or digital, so that's why we need it. And basically what it does is, if we have a 1 here, it chooses this voltage plus Vref. If we have a 0 here, it chooses minus Vref. And then as I said before, here we have a 1 or a 0. So the way this conversion works is basically you do lots of loops, and at the end here you have a stream of m bits. As you can see, it's written. So the more bits you have, it doesn't the average of the bits, and it approximates the V in. So in that way we've successfully managed to do the conversion. Okay, I hope you like this video, and if you have some questions, ask in the comments, and see you in the next one.